Hello everyone and welcome back to Diksha Karnataka YouTube channel, and you are watching KCET 60 out of 16 Physics Series, where I am trying to help you to achieve the dream 60 out of 60 in KCET 2025. So if you are preparing for KCET 2025, this is a must watch, and today we are going to complete the chapter Nuclei. Here in this discussion we will complete whatever remaining part of Nuclei chapter. Also we are going to discuss a few of the previous year questions which are left, because most of the important portion that used to come from this chapter are now deleted. So we are not going to discuss any of the deleted questions because that might create some confusion amongst you. So I will only solve the questions which are there in your current syllabus. Later on in some later part of our discussion, I will solve some questions which are part of your current syllabus, and important questions. They are definitely not PYQs, but they will be important questions from this chapter. We will combine a few chapters together and then we will solve some important questions. Now today I will discuss mainly about nuclear forces, some part of radioactivity, because most of the radioactivity part is deleted, then nuclear fission, nuclear fusion, and obviously the PYQs. And every Sunday, as you know, we are organizing a grand test calling it KCET Premier League, and if you want to participate in it, it's absolutely free. Only thing that you have to do, you have to spend some of your time and click on the link given in the description and join our WhatsApp group, join our WhatsApp brigade, and from there you can download the question paper every Sunday. We are giving you a grand test on physics, chemistry, maths, biology for NEET aspirants as well. So only thing that you have to join is our WhatsApp group and download the question paper, solve it, and check the answer when I am giving you the solution at night. Now today I will be discussing nuclei part 2. So let's see what all are there in today's discussion. So obviously we will start with nuclear force, a very important force. Then we will discuss about radioactivity. Then we will discuss nuclear fission. Then we will discuss nuclear fusion, and lastly we will discuss PYQs. Okay, clear? Now let's start with the first topic of the day, nuclear force. So to bind the nucleus together, there must be a strong attractive force of a totally different kind. Why so? Because we know that inside a nucleus, we have learned that inside a nucleus there are positively charged protons and they are very close to each other. For example, if you consider the yesterday's example of gold, we have seen that in a gold nucleus there are 79 of the protons are there. 79 protons inside only gold nucleus. There are heavier nuclei where more number of protons are there. So if we are wearing a gold ring, that means inside each and every atom of that gold ring there are 79 protons. Now 79 protons, we know that the distance between them is very small, that is 10 to the power of minus 14 range. So the Coulomb force that is between these two protons will be very high. The distance you can imagine almost very close to zero, not exactly zero but very close to zero, right? So we know that Coulomb's law varies almost inverse square, right? So Coulomb force will be very high between two protons, so they will repel each other with a very high force, right? So if this force is very high, then the nucleus will break apart, so we will not be able to wear our favorite gold ring. So but gold exists, we can wear gold ring. In fact, many other, all the atoms that we are seeing in our surrounding, they are all consisting of more than one proton except hydrogen. Okay, so they all exist because there must be something which is preventing the nucleus from breaking down. Now what is that force? So that force should be not something that we know so far. Okay, so far we have learned about, first of all, gravitational forces, we learned about Coulomb forces. This is also different kind of forces. Also magnetic force, we combine it to Coulomb force and we say it is electromagnetic force. So electromagnetic force, gravitational force. Okay, frictional force is a kind of force, but it can be explained using gravity, because gravity is essential for friction to be effective. So frictional force is a part of gravitational force. Okay, if there is no gravity, there will be no friction, obviously, right? We have seen that this is a part of the component, or some other external force has to be applied, some physical force has to be applied, right? Frictional force can be explained using gravity, but here this force cannot be explained neither using gravity, because gravitational force is heavily dependent on mass, and as we know, nuclear force, objects are very, very small in mass, so their gravitational force is almost zero. So we cannot even consider gravitational force. If someone is saying, sir, there is a gravitational force between the neutrons, that's why they are sticking close to each other, but their gravitational force is almost zero, because their mass is very 10 to the power of minus 27 of the order for a proton, right? So you cannot even consider gravitational force as well. So only thing that is left is there should be some new force acting between two protons, that is binding the protons together, right? So what is that force? That force is called nuclear force. Very important concept to be understand. So it must be strong enough to overcome the repulsion between the positively charged protons and to bind both protons and neutrons into the tiny nuclear volume. So nucleus is very small, so something is there who is pulling everything together, something is there which is binding everything together in that small space of nucleus, right? So that force is called nuclear force. Now in fact, in nature there are 4 fundamental forces. Okay, even though it was there in your previous syllabus in the first chapter of first PU, but now that chapter is deleted, but I will give you the names of those 4 forces. First of all, gravitational forces, obviously we know about gravitational forces. Secondly, electromagnetic forces, we know about electromagnetic forces, force between two charges, force between two magnets, that is for electromagnetic forces. And there are 2 more forces. One is strong nuclear force, okay, and there is another 4th type of force which is called weak force. Okay, we will hardly discuss about weak force and nuclear force also. We are only discuss about its properties, basic properties, but not in detail about nuclear forces. But you should know that there are 4 fundamental forces. All other forces are basically part of these 4 forces. Mainly in our observable universe, gravitational force and electromagnetic force are predominant. That is what we observe in our day-to-day life. To observe nuclear force, you have to go inside the nucleus, okay, and you can see sometimes if you have to detonate a nuclear bomb to experience the nuclear force, okay, which is completely absurd. It is happening inside the nuclear reactor. We are breaking apart, we are breaking the nuclear force and we are extracting something, and that is happening. We will discuss briefly about that in today's lecture. But other than that, nuclear force is not visible to our eyes directly, okay. Indirectly, obviously, all the rigid bodies, they are rigid because of there is a nuclear force existing inside the nucleus that is staying the nucleus intact, and because the nucleus is intact, we can walk on the surface, we can talk, we can walk, everything is possible because of the nuclear force, but it is inside as a hidden force, right? Now let's discuss about the properties of nuclear force. So what are all those properties? The nuclear force is much stronger than the Coulomb force acting between charges or the gravitational forces between masses. Okay, obviously nuclear force is the strongest force in the nature. Okay, nuclear force is the strongest force in the nature. That's why it is sometimes called strong nuclear force. Okay. The nuclear force between two nucleons falls rapidly to 0 as their distance is more than a few femtometers. Okay, femtometers we have discussed 10 to the power of minus 15 meters. That is 1 femtometer or 1 Fermi. Okay, sometimes it is called Fermi, sometimes it is called femtometer, right? So if the distance is increases, if you increase the distance more than few femtometers, the nuclear force becomes 0. So it is a short range force. It is called a short range force. Okay, so this leads to the saturation of the forces in a medium or a large sized nucleus, which is the reason for the consistency of the binding energy per nucleon. So if you see the binding energy of the nucleon graph, the graph initially starts with a low volume, but it becomes almost constant. Why? Because the nuclear force is saturated. Okay, nuclear force is constant throughout the volume. That's why, because it is a very short range force. So suppose for the example, you are sitting in a classroom of 60 students. So consider that all the 60 students are neutrons and protons. Okay, and whatever the students discussing in the first bench, okay, whatever the students are discussing in the last bench corner, they are not able to hear each other because they are whispering to each other. So you can consider that nuclear force, even though it is very strong, they are like a whispering force. Okay, so they are talking between two students in the same bench. Okay, but whoever is sitting last bench, they are not able to hear whatever they are talking, right? So nuclear force is like that. Okay, now, but they are interacting with each other, so that the force is still there and it is constant. Throughout the classroom there is a silence, so that is the basic requirement. The nuclear force between neutron to neutron, proton to neutron and proton to proton is approximately the same. So previously Coulomb force was what? Coulomb force was when it is between two charges. There was never a force between two neutral objects, right? But in case of nuclear force, even neutron to neutron interaction is possible. Okay, neutron to neutron interaction is possible. Okay, this is little complex force, not so easy to explain. A lot of quantum mechanics, quantum theory is required, but I am not going to discuss that in this class. Obviously, the nuclear force does not depend on the electric charge. Obviously, it does not depend on electric charge. So that is the important part. That's why neutron-neutron interaction is possible. Now, if you plot the potential energy, okay, with respect to the distance, then you will see that potential energy falls rapidly to some value when it is this is between two nucleons, by the way. So it can be between two neutrons, between proton and neutron, between proton and proton. If you plot the potential energy between any two nucleons, you will see that the potential energy drops to negative value very quickly. That means the nuclear force is very strong. Potential energy negative means the energy required to separate them is very high. That means the force is very high. But after some time, say this is a femtometer, the distance scale along x-axis is in the femtometer range. Okay, so it is very low when the distance is less than 1 femtometer. As soon as you are going to 2 femtometer, that is only 2 femtometer, 2 times 10 to the power of minus 15. So the force is slowly going to 0, and as you can see at 3 femtometer it is completely 0. From 3 femtometer onwards the nuclear force is absolutely 0. Now this graph is important because it came in your previous year questions. Once we will discuss that question, so you should remember that this graph, this is in MeV, okay, this is in femtometer, okay, and this is in negative value. Okay, this interaction, this value is going to negative value. Okay, you have to remember these three things, because there are different kinds of same plots. They will give you, one times they will give you in meters, one times they will give you in EV, sometimes they will ask you KeV, but you have to read the scales of the x and y axis, and you have to read, okay, if it is going to negative or not. Okay, so this is the things that you have to remember. Now let's solve yesterday's homework problems. The energy required, energy equivalent to a substance of mass 1 gram is. So they have asked you to find the energy equivalent. So if you destroy 1 gram of mass, how much energy you will get? That is the energy equivalent. Now to solve this, what equation we will use? Obviously we will use E equals to mc square. Now remember that in this equation m is given in kilograms, okay, and c is in meter per second. So we have to first 1 gram is given. So 1 gram we have to convert it into kilograms, dividing by 1000, right? Next what we have to do, we have to find c square. C is 3 times 10 to the power of 8, we know that, whole square. So 10 to the power of minus 3, 1 by 1000 is 10 to the power of minus 3 times Now if you complete the whole square, 3 square is 9 times 10 to the power of 8 whole square is 10 to the power of 16, right? So it will be 9 times 10 to the power of 13 joules. Now if you check the options, only one option is correct, that is 9 times 10 to the power of 13 joules. Okay, all other options are incorrect. So this is a small problem, easy problem also from your previous year question. So I hope you enjoyed this question and are able to solve this question. Now next question is, binding energy of nitrogen nucleus in 714 is given by M equals to, okay, you have to find the binding energy of the nitrogen nucleus given the mass of the nitrogen nucleus is 14.00307 U. So how can we solve it? Okay, as we said, we will use the approximated value of mass of proton to be 1.007 U and mass of neutron is 1.008 U. Okay, if you remember these values, it is sufficient. Okay, now what will be the mass of the constituents? First we have to find the mass of the constituents. Mass of the constituent means how many protons are there. So 714 means proton should be 7, okay, and neutron should be 14 minus 7, that is again 7. So the total mass of the constituents, let's say M total, will be 7 times 1.007 plus 7 times 1.008. Now let's complete this addition. 7 times means 7.0, 7 sevens are 49, so 1 4 will come here, 49 plus 7 1 is 7 dot 0, 7 8 is 56. So just add them. So it will be 5 in hand 1, 4 5s are 9, 9 plus 1 10, so 105, 14.105. So as you see, the mass of the constituent is more than that of the mass of the nucleus, right? So the rest difference in energy should be conserved as binding energy. So binding energy is delta M C square, right? First of all, let us calculate the delta M as well. Delta M is, what we have to do, we have to minus the mass of the nucleus, that is 1.003. okay, you can ignore the rest of the part, so it will come out to be 2.102. okay, so delta M is 102 U. okay, so remember the unit, okay, because this is very important. Delta M is 0.102 U. Right, now we have to apply the concept that I taught you yesterday to convert it directly from U to energy EV. We have a shortcut, right? What is MEV? Sorry. So 1 U is equals to 930 MeV, right? 1 U is equal to 930 MeV. So we will just use that value. Okay, we will not use the value of C square, that is not required. We will directly convert it into MeV. (102) times 930 MeV. So as you can see, 102 by 1000 times 1000 almost equals to almost it will be 102 MeV. Okay, it will almost equals to 102 MeV. How I got that? So you can write decimal 102 is equals to 102 divided by 1000, right? 3 decimals are there. Now if you consider the approximated value of 930 to be 1000, okay, then it will be 102 MeV. Now you might be thinking that the correct answer is very close to 1047.7 MeV, but actually we have increased this value. So actual value should be 85 MeV. Okay, very interesting question, because we have increased 930 to 1000 and we received 102 MeV. That means we have to understand that the actual value should be less than that. So less than that is 85 MeV. 85 MeV is the correct answer for this question. Okay, if this question comes again in your upcoming exam, they will give you rationalized value, so that even if you do a lot of approximation, your answer will be you will not be able to think too much about the answer. You can answer this question as long as you are applying the concept correctly. Okay, this was a very old question, that's why the answers used to be very close, because that time calculators were allowed. Nowadays calculator is not allowed, so you are not going to solve this question without using calculator. Right, now let us discuss about radioactivity. Radioactivity was a nuclear phenomenon in which an unstable nucleus undergoes a decay. What is the meaning of decay? Decay means it slowly dies. Okay, slowly dies, it loses material, it loses something, and then it dies. Okay, so decay means, like for the example, if you leave something in nature for a long time, it slowly decays. Right, our tooth decays because after some time with the natural weathering, it loses its shine, it loses its newness, and but for some atoms it is happening automatically. Even if you keep it inside the room, it will slowly dies out, because it is called radioactive. So for example, uranium is a radioactive material, radium is a radioactive material. There are multiple radioactive materials. For example, thorium, largest deposit found in India, so this is also a radioactive material. Okay, radioactive material means they decay automatically even if they are kept in a safe box, kept in a storeroom. Okay, and they are very, very harmful for us. So if you see some radioactive material, don't touch it, stay away as far as possible, because it will slowly make your body also decaying and you will die. So stay away from any radioactive material. Now, radioactivity is a nuclear phenomenon. What is the meaning of that? The nucleus slowly decomposes. Okay, separated nucleus slowly loses its shine, and it gives you a new material. Sometimes it gives you a new material, sometimes it just gives you a lower energy material, lower energy nucleus. Okay, now three types of radioactive decay occur in nature. There are three different types of decay. First of all is alpha decay. Okay, there used to be a lot of questions based on this alpha decay, but nowadays there is no question based on alpha decay. As we have seen in Rutherford's experiment, that there was a source which was a source of alpha particles. So basically that material, whatever was used, bismuth, so that emitting alpha particle, because that is decaying alpha. Okay, so that material was in the state of alpha decay. Okay, so alpha decay was happening. So once alpha decay is happening, that means helium particles, okay, helium nucleus 24He is being released. Okay, helium nucleus means it has to be doubly positive. Okay, doubly positive, because helium has 2 electrons. Nucleus means those 2 electrons are taken out, only the nucleus is coming out of the material, and that is why it is called alpha decay. Okay, next is beta decay. Beta decay is interesting, in which electrons or positrons, okay, are emitted from the nucleus. Okay, we should be remembering that even though these electrons and positrons are coming out of the nucleus, there is no electron or positron present inside the nucleus. Okay, this is a process. Okay, this is a process through which nuclear emission is happening. This is a complex process, but you should remember these electrons are not free electrons inside the nucleus. Okay, electrons, there are no electrons inside the nucleus means there are no free electrons inside the nucleus. Okay, it can generate through various processes, like in radioactivity, through radioactivity, but there will be no electrons freely present, freely roaming inside the nucleus. Okay, basically as we said, as we have observed in decay of a neutron, Okay, if you remember, yesterday I discussed neutron decays into a proton and an electron. Okay, that electron is emitted as a form of beta decay. Okay, if sometimes nucleus is not able to withhold all the materials, all the constituents inside the nucleus, and that is why it decays so that it becomes stable. This is a way of attaining stability of the nucleus. Okay, some nucleus is so large, they have lot of protons and lot of neutrons inside it. Okay, and it is not possible for the nucleus to hold on to everything that it has. Okay, so slowly one neutron will decay into proton and an electron, and that electron will come out. Okay, so these are the things. Similarly, sometimes proton will decay and it will give out one electron. Okay, one positron. Okay, so what is a positron? By the way, positron is a particle which has the same mass as electron. Okay, positrons are the particles which have same mass as the electron, but it has the exactly same charge as electron but in opposite sign. Okay, so charge of a positron is plus E and mass of positron is Me. So it has the charge similar to an electron, or you can say similar to a proton, but charge is exactly same as proton, mass is that of electron. Okay, so that is called positrons. Okay, there are anti-particle of electron, anti-electron, sometimes you can call it anti-electron or anti-particle of electron. Okay, but they are being called as positrons. Okay, gamma decay, in which high energy, okay, hundreds of kilo electron volt or more photons are emitted. So when electrons are emitted, energy is emitted as a form of radiation, okay, as a form of electromagnetic radiation, that is called gamma radiation, which is very harmful for our bodies. Okay, gamma radiation is not very safe. Okay, it is used to treat cancer. Okay, if you have cancer in your cells, okay, there is some gamma active material is placed there, so that gamma radiation penetrates your body and kills the cancer cells. But in that process, your healthy cells in your body also dies. So that's why this is not very safe way to treat cancer, but this is the last way to treat cancer. Okay, one of the last way, we call it chemotherapy. Okay, chemotherapy means there are different types of rays, but one of the rays, gamma ray. Gamma ray is passed through the cancerous cells so that they die. Okay, cancerous cells die in the process, and then your body becomes healthy again. Okay, so this is one of the process, and these are the three process. There used to be a lot of equations, lot of calculation based on this three kind of decays, based on the different parts of the radioactivity, but those are all deleted now. So don't worry about everything that was there in your previous year questions. Some radioactive questions, radioactivity related questions, they are not part of your syllabus, so you don't need to solve it for KCET 2025 exam. I am clear about that. Okay, so don't waste your time solving radioactivity related questions for KCET 2025, because that is not part of the syllabus. It will not come in your 2025. Even if it comes, then you can consider it to be a bonus question, or you can consider it to be a deleted question. Okay, they will be either deleted or they will be either treated as a bonus question. Okay, now nuclear fission. Okay, nuclear fission, we will discuss that. When a heavy nucleus is bombarded, heavy nucleus means someone who is heavy, the weight is heavy, so the size of the nucleus is very big. So I gave you one example in the radioactivity chapter part, that there are some nucleuses which are not able to hold on to all of the nucleuses, all of the nucleons, right? So some protons are going out, some neutrons are going, neutrons are separating, some protons are saying no, I will not stay inside the nucleus. So they are either splitting into the halves, or they are emitting particles. Okay, now during that process, to accelerate that process, this is a natural process. Okay, the alpha decay, beta decay, gamma decay, they are natural processes. All of them are natural processes. Now to accelerate that process, okay, this is very, as you have seen, the gamma rays are emitting, coming out, alpha rays are coming out, even beta rays are coming out, right? Even though beta and alpha are not rays, not electromagnetic rays, only gamma ray is electromagnetic ray. That is also one important point for objectives. Okay, alpha and beta are basically particles, but they are very high speed particles, that's why they are called rays. Okay, but gamma ray is actually truly electromagnetic radiation, and it has a very high penetrating power. It can penetrate very thick metal plates as well. Okay, now to accelerate the process in a controlled environment or in uncontrolled environment, what we have to do, we have to bombard it using nuclear particles. For example, a neutron. If I bombard uranium with a neutron, the process of radioactive decay starts manually. So we can do the radioactive decay process manually, and that process is called nuclear fission. That is no longer a radioactivity. Radioactivity is a natural process, but when we do that same process manually by bombarding nuclear particles such as proton, neutron and alpha particles, etc., it breaks into smaller stable nucleus, and they are called daughter nucleuses. Okay, so daughter nuclei are basically the process after. It can be one nucleus, it can be two nucleus, it can be more than two nucleus. Okay, after the decay process is over, whatever is left, that is called daughter nucleus. Okay, now let's see one example. So here we have taken one of the heaviest thing, that is uranium 92-295. Now we have bombarded it using a neutron. Okay, after the bombardment is over, okay, we can see that it is not 295, sorry, it should be 235, uranium 235. So uranium 235, what is happening here? After this neutron is bombarded, okay, there are beryllium and krypton. There are two materials which are being produced, and there are also 3 neutrons are produced, and a lot of energy is produced. Okay, a lot of energy is released. This energy is collected to inside the nuclear reactor, and then that energy is converted into electricity, and then they are being transferred to our homes. If there are many nuclear power plants inside India, outside India, all over the world. So this is the process which is being performed inside a nuclear reactor. Okay, so we have this is called fuel. Okay, this is the fuel. So this is being bombarded with neutrons. Okay, and that fuel is being now splitted into different materials, and they are stable. So after this process is over, okay, we are getting extra energy. That energy is then converted into our useful form of energy, that is electricity. Now the fragment products are radioactive nuclei. These are also radioactive nuclei. Okay, they emit beta particles. They emit beta particles in succession to achieve a stable product. So they are radioactive in nature, but they are not as active as uranium, so we cannot break it apart further to get more energy out of it, but they naturally emit beta particles and then they become stable. Okay, that takes long time. That is a very long process. Radioactivity is a very long process, whereas nuclear fission is immediate process. Okay, when we want the energy, we will just have to bombard it. Okay, so the source of the energy in nuclear reactor, this is the source of the energy in the nuclear reactors which produce electricity, is nuclear fission. Okay, the enormous energy released in the atomic bomb comes from the uncontrolled nuclear fission. So if you remember Hiroshima and Nagasaki, where they dropped 2 atomic bombs, even whenever there are 2 big countries are fighting, they always say there is a threat of nuclear invasion, nuclear bombs explosion. So that is nothing but, and even in your spy films, movies, you may have seen that people are talking about nuclear bombs, etc., nuclear warhead. They are basically nothing but this nuclear fission process. Everything is there. Only thing that you have to do, you have to unleash these neutrons so that these neutrons strike the uranium stored inside the bomb, and then it will start bursting. But in that case, there is no control. We will release the neutron immediately, and once the neutrons are released, they will start reacting, and then there will be bomb blast. Okay, but that is uncontrolled way. In uncontrolled way, a lot of amount of heat energy will be generated, which is sufficient to evaporate even human body. You will not find any human remains. Okay, if a nuclear bomb is dropped, suppose I am talking here, someone dropped a nuclear bomb here, then you will not even find my body. Okay, because it will be evaporated completely, including my bones. Okay, so this is a very dangerous thing. So don't ever try to play with atomic bomb. Okay, I know, just joking. Now let's look into one more thing which is very interesting, is called nuclear fusion. Okay, so I discussed briefly about fusion. Fusion means when you combine together. Fission means when you are dividing. Okay, you are breaking it apart, that is fission. Fusion means when you are joining. Okay, so what is fusion? When two light nuclei, light means lighter, okay, in less amount of nucleons inside the nucleus, they are called light nuclei. Okay, so when two light nuclei fuse means they combine to form a larger nucleus, energy is released since the larger nucleus is more tightly bound. Okay, so this is a very convenient way of producing materials which has very less radioactivity. Okay, so if you are wondering about nuclear fission is easy to do, easily doable. Okay, but the end product is also radioactive, which is harmful. Obviously radioactivity is harmful, as I told you, but nuclear fission you are merging two lighter nuclei to form a heavier nuclei, and that heavier nuclei is not radioactive. Only thing is this is more stable. More stable means it requires less amount of energy, the extra amount of energy is being released. Okay, extra amount of energy, whatever energy was there in lighter nuclei, that is being released and that energy is collected and then that is used for useful work. But still so far we have not been able to achieve this process without requirement of very high amount of energy. So for example, I am giving you one example. Okay, so this is called hydrogen bomb. Okay, it was dropped in one of the Hiroshima and Nagasaki site. To achieve that, you have to detonate a nuclear bomb first. Okay, to achieve this you have, so for example, to achieve this you have to have a nuclear reactor that is producing huge amount of energy, and that energy then can be used to fuse them together, and that in turn will produce much more energy. Okay, so this process is not possible without spending a lot of amount of energy, which is not possible right now. Okay, so that is why this is not been able to be achieved by us. Okay, and as you see in this process we are merging two hydrogens. Okay, and we are getting a deuterium. Okay, two hydrogen are merged, one deuterium, one positron, one neutrino, and some energy is being released. Similarly, if you combine 4 hydrogens, okay, and 2 electrons, then you will achieve a helium nucleus. Okay, so 4 hydrogens are being merged to get a completely new element. So 4 element of hydrogen, okay, and merging it, and you are getting helium, which is a new element. Okay, and then this is a lot of amount of energy is also released. This is the process, it is happening constantly in our star. Any star, if you see, they are automatically merging the hydrogen into helium, and then in the process whatever energy is being produced, that energy is being released towards us, and we are feeling the warmth of the sun. So this is happening inside the core of the sun, inside the sun for millions of years, and it will continue to happen millions of years. After this is over, then heliums will start merging, then they are continually merging, and all the elements of the periodic table will be formed till iron. Okay, as soon as iron is formed inside the core of a star, the star do not able to continue the fusion process anymore, and the star dies. Okay, this is the life cycle of a star. So I taught you the life cycle of a star, which is, I think maybe you find it interesting, that's why I taught you. Now let's solve previous year questions. Only few are there, so don't go anywhere. Let me solve this for you. A nuclear reactor delivers a power of 10 to the power of 9 watt. Okay, the amount of fuel consumed by the reactor in 1 hour is. Now nuclear reactor directly is not part of the syllabus, but this problem is does not require any knowledge of nuclear reactor. You can solve it using the Einstein's relationship, that is E equals to mc square. Now they have asked you to find the amount of fuel. Amount of fuel means, I said amount of fuel means this m you have to find. Now in this case they have given you the power is 10 to the power of 9 watt. 10 to the power of 9 watt. What is joules per second? So first of all we have to calculate how much fuel is required for 1 second, then we will multiply it with 60 seconds for 1 minute, and then another 60 minutes to find it for 1 hour. Okay, so that is the conversion that we have to do at last. But first of all, we know that energy is given in watts, and mass, say m, and c is meter per second, so everything is fine. So we will just simply do it. Okay, so mass of the fuel per second is 10 to the power of 9 divided by 9 times 10 to the power of 16, right? So it will be 10 to the power of minus 7 by 9. This is the mass of the fuel required in 1 second. So how much mass is required for 1 hour? Say that mass is capital M. So that mass will be 60 times 60 times M, right? So just put the values, 60 times 60 times 10 to the power of minus 7 divided by 9. So 9 means 3 3s are 9, 3 20s are 60, 3 20s are 60. Now it will be 4 times 10 to the power of minus 5. Okay, 4 times 10 to the power of minus 5 kilograms. 4 times 10 to the power of minus 5 kilograms, or we can write this as 4 times 10 to the power of minus 2 grams. Okay, it will be reduced by minus 3, right? So, or we can write this as 0.04 grams. Okay, so as you can see, only by destroying 0.04 grams of mass in 1 hour, you can produce 10 to the power of 9 watt energy, that is 1000 megawatt, 1000 megawatt. Okay, that is 1 gigawatt energy. So this is a huge energy. Okay, 1 gigawatt energy is a huge energy. So that is a big power plant, and only mass that you need to destroy is 0.04 grams, which is very small, right? So even though it looks like very prospecting, but it is not so easily achievable. So that's why we have very limited access to this, and nuclear power plants, as I said, are not super safe for future. They are not future proof, even though they have their uses, they have their utilities. Okay, for example, nuclear submarine can stay underwater for a long period of time. Okay, nuclear powered warships, they can stay inside the sea for a long time, right? But nuclear energy, after it is produced, if you are producing it for masses, okay, there will be a lot of waste produced. That waste is not very helpful. You have to store it somewhere because it is radioactive. So that is why nuclear power plants are not so popular, because of the waste disposal of the main thing. That is the main thing, right? Also there is a risk, like if you have heard about Chernobyl, where it was exploded, right? So that's why nuclear reactors are not so popular, even though it is very, very cost effective. Now as I said, I told you this question: which graph of the following diagram correctly represents the potential energy of a pair of nucleons as a function of their separation? So what you have to remember, first of all, the energy, the graph C. If you see, there are 3 graphs which are of the same order. Obviously this graph is incorrect. If you remember the pattern, this is not the pattern. These 3 are the patterns. Pattern wise, these 3, all of them are correct. Okay, but which of them is actually correct? First of all, I told you to check if it is given in MeV. It is given in MeV? No. Is it given in MeV? No. Only this is given in NeV, and this is given in femtometer. So obviously option D is correct. And in case, so here you have found it only using MeV only, right? Now in case this is also given in MeV, then you have to check the R as well. Here R is given in meters, here R is given in femtometers. So this is correct, but this is wrong. And in this case, these 2 things are matching. Only for MeV and FM, both are matching. So correct answer is option D. Okay, you have to be careful. This is a very tricky question. Even though very simple question, you have to be careful. Now last question: during a beta decay, a neutron in the nucleus decays emitting an electron. Okay, a proton in the nucleus decays emitting an electron. an atomic electron is ejected, atomic electron does not exist, so it is not possible. An electron which is already present within the nucleus is ejected, obviously there is no electron inside the nucleus, so these two are cancelled. Only possibility is either neutron is decaying or proton is decaying. Now as we know, proton is stable, generally does not decay in normal circumstances. It decays when you are bombarding it with something. Okay, normally a proton does not decay on its own, so only thing is a neutron can decay and it can emit an electron, that is called the beta particle, right? So we have end of this discussion today, and if you want to get all the updates from the physics channel, then you have to go to the playlist and bookmark it, so that whenever a video is uploaded you get the notification. Also follow our channel, subscribe to our channel, click on the bell icon so that you don't miss on the notification. And if you have not yet subscribed to our channel, don't forget to subscribe to our channel and share it with your friends, and join our WhatsApp group. The link is given in the description, and I will be back with a new video tomorrow, that is semiconductor, last chapter of your second PU. I will be continuing with semiconductor for 2 to 3 days, then we will conclude that chapter as well. So for next week's KPL, if you are wondering, next week KPL syllabus will be based on nuclei and semiconductor electronics. Okay, apart from that there will be nothing. From next week onwards, after this KPL is over, we will start with first PU, and every week we will review one second PU chapter and the first PU chapters, whatever we have completed as for a topic for KPLs. Okay, so KPL will be based on nuclei and semiconductor electronics for this Sunday. If you are preparing, prepare hard, prepare well. I will be back with semiconductor electronics tomorrow. Till then, bye bye.